This video is going to give a brief overview of functions, including function notation, the difference quotient, and some graphs of our basic toolkit functions. So a function is basically some type of operation that maps a set of inputs. And our inputs, typically in algebra, we use the letter X to represent inputs, to a set of outputs, which we might use the variable Y to represent. However, functions can be given as words, tables of values, graphs, and equations. So a function maps a set of inputs to a set of outputs, such that every input is mapped to exactly one output. So for example, I've got a couple of relationships. My first one, the input is going to be a student, and the output is their birthday. Is that an example of a function? So if it is a function, every input, which in this problem is a student, can be mapped to only one output or only one birthday. And yes, this is a function because every student has only one birthday. Right? Everybody has only one birthday. Nobody's going to have two different birthdays. So this is an example of a function. Whereas if we make our input fast food restaurant and our output location, is that an example of a function? Again, to be a function, every input can have only one output. And if you look at my table, and you just kind of think about our fast food restaurants, the input of McDonald's in this table has two different locations. One in Lakewood, one in Denver. There's probably other locations as well. And then our second input, Subway, also has multiple locations. So this is not an example of a function because our inputs are mapped to more than one output. My third example is just numbers. We're going to just call our inputs x's and our outputs y's. Is this an example of a function? For it to be a function, every input, every x, can only correspond to one output or one y value. And this is a function because the number 7 only corresponds to 3. The number 8 only corresponds to 11. 5 goes with -6. 10 goes with 3. It doesn't matter if you get the same output more than once. You don't want to see the same input more than once going to two different outputs. So this third example, yes, it is a function. Every input goes to only one output. What if we're given an equation? Equations can be functions as well. So same question, but now we're asking, is y a function of x? So the way this is worded is telling us that x is our input and y is our output. And it's standard to use x for the input and y for the output. So we've got 3 different equations. The question is, are these functions? Well, the first one, y equals 5x plus 11. Yes, that is a function. We could say it's a linear function because if you plug any number you want in for x, you're only going to get one y value. For example, if I put -2 in for x and I solve it, I get one answer or one y value. And in fact, if an equation is solved for y, it's of the form y equals, and it's like a linear or polynomial, looks pretty simple. It should be a function. You plug a number in for x, you get only one output for y. So the second one, y equals x squared, is that a function? Yes. We could call that a quadratic function because it has an x squared. But the idea is the same. If I plug any number in for x, I get only one answer for y. For example, if I plug -4 in for x, y would be -4 squared, which is 16. The important idea is when I plug something in for x, I get only one y value. Last one, y squared equals x. Is that a function? Now I notice that one is not solved for y. And so let's think about what happens if we plug in something for x, if we plug in an input. If I plug 4, for example, for x, Now I've got the equation y squared equals 4. This is actually going to give us two different y values, 2 and negative 2. So this is not going to be a function. My input corresponds with more than one output. Another strategy you can use to see if this is a function is you can try to solve for y. We've got y squared equals x, so we could take the square root of both sides. But when you're solving an equation and you take the square root of both sides, you have to put a plus or minus there. So you get y equals plus or minus root x. And that plus or minus indicates that there's two different y values that correspond with our x values. All right, what if we have a graph? I have two graphs on the screen right now, and the question is the same. Is y a function of x? X is my input, y is my output. So we're thinking about the same thing. If we pick an x value in, how many y values go with each x value? So if I pick any number for x, and I find the corresponding y value, there is only one y value that goes with every single x value. If I pick any number for x, say I pick negative 4, when x is negative 4, y is positive 4, only one y value. So this is an example of a function. Now, if we compare that to the circle that I have graphed over to the right, there are some x values I can pick. For example, if I pick x equal 1, notice there are two different points on the graph of that circle that correspond with x equal 1. When x is 1, y can be, it's hard to tell exactly what it is there, maybe 2 point something, 2.7, or negative 2.7. So there are x values on this circle that correspond with 2, or more importantly, more than one y value. So the circle is not a function, but this kind of V shape is a function. A kind of quick way that you can determine whether a graph is a function or not is something called the vertical line test. If you have the graph of a function and you draw a vertical line through it, a vertical line will cross the graph of a function at most one time. I can see that with this V-shaped graph. If I draw vertical lines through it, no matter where I put those vertical lines, they will only cross the graph once. Whereas if we compare that to our circle, if we draw vertical lines through the graph of that circle, they're going to cross in many places 2 times, more than once. So the circle is not a function. The graph to the left is a function. The next thing I'd like to go over is function notation. When we are working with functions, we often replace the output, which I'm calling y, with the symbol f of x. So these two symbols are interchangeable. Y and f of x mean the same thing. Within this notation, the thing inside the parentheses is telling us what the input is. So this x in the parentheses is telling us that our input is x. But this entire symbol f of x stands for the output or the y value. And I guess the f is just the name of the function. We have function f, we put an x value in it, and we get an output or a y value. So let's see how that works with both a graph and some equations. So I have the graph of a function shown to the right. This is the graph of y equals f of x. Let's use the graph to find the following. So the first thing I want to find is f of negative 2. This is asking me to find the function value when x is negative 2. So again, the thing inside the parentheses is the x value. When we put that f in front of it, it's asking us to find the output or the y value. So f of negative 2 is asking us what is the y value when x is negative 2. So going to my graph, if x is negative 2, I go up to the curve. The y value is positive 2. So f of negative 2 equals positive 2. That's telling me when x is negative 2, y is positive 2. What is f of 3? So now this is asking, what is the y value when x is 3? The thing inside the parentheses is your x value. So I go to my graph. I find x equal 3. I go up to the line. What is the y value? Oh, looks like the y value is also 3. So f of 3 equals 3 is telling me when x is 3, my y value is also 3. Finally, the last question, for what values of x, so now we're finding x, does f of x equal 2? This f of x symbol stands for y value. This third part is asking us, when does the y value equal 2? We can replace f of x with y. So when is the y value equal to 2? So I just drew a horizontal line at 2, and I can see that it intersects at 2 different places. So I've got 2 different x values, negative 2 and positive 2. So for what values of x does f of x equal 2? At x equal 2 and x equal negative 2. We can do the same kind of thought process if we're given an equation. So now we've got the function f of x equals 3x minus 5. Find the following. Find f of 2. So first of all, our function f of x equals 3x minus 5 is equivalent to the equation y equals 3x minus 5. The f of x is the same as our y value. So f of 2 is asking us, what is y when x is 2? The thing inside the parenthesis is the x. The f part says we're finding that function value or the y value when x is 2. So to answer that question, I just have to plug 2 into my function. F of 2 equals 3 times 2 minus 5, or 6 minus 5, or 1. So when x is 2, y is 1. F of 2 is 1. The second part, f of negative 4, is now asking us, what is the y value when x is negative 4? So to find f of negative 4, I'm going to put negative 4 in for x. So 3 times negative 4 minus 5. That's minus 12 minus 5, or negative 17. So that's telling me when x is negative 4, f of x is negative 17. When x is negative 4, y is negative 17, or f of negative 4 is negative 17. The third question says, find all values of x such that f of x equals 5. So now we're trying to find the x values, and they're giving us the y value. They're telling us f of x, the output, the y value is 5. So I'm going to put 5 in for f of x. That gives me 5 equals 3x minus 5. And I can solve this equation. I have to add 5 to both sides. That gives me 10 equals 3x. Divide by 3. X equal 10 thirds. So when x equals 10 thirds, f of x is 5. Or in function notation, we could say f of 10 thirds equals 5. Finally, my last example here says, find f of 2y. It's okay to put variables or expressions into functions. To find f of 2y, I'm going to do a process very similar to what I did in the first and the second part. I just have to take the 2y, that's my input, and plug that in for x. So 3 times 2y minus 5 is 6y minus 5. So we can take an expression, plug that into our function, and I ended up getting an expression as my answer. So for the last one, f of 2y is 6y minus 5. Let's run through another example that's similar, just to get a little bit more practice. F of x equals 2x squared minus 3x. Find the following. So for the first part, we're going to find f of 2. So we are trying to figure out what is the y value when x is 2. So f of 2, we're going to put 2 in for both of the x's. So I get 2 times 2 squared minus 3 times 2. That's 2 times 4 minus 6. 8 minus 6 are 2. So f of 2 equals 2. When x is 2, the output or the y value is also 2. All right, what about f of negative 1? Same process. I'm going to put negative 1 in for both of the x's. 2 times negative 1 squared minus 3 times negative 1. Let's see, that's 2 times 1. And then minus 3 times minus 1 is plus 3. So 2 plus 3 is 5. When x is negative 1, our output or our y value is 5. The third part asked us to find all values of x such that f of x equals 5. So this part, we are solving for x now. Find x, and they are giving me the y value. When f of x equals 5, means I have to put the 5 in for the f of x. So I've got the equation 5 equals 2x squared minus 3x. This is a quadratic equation. I'm going to set one side to 0, so I minus the 5 to bring it over to the right. And now I have some choices. I can solve this by factoring. I could use the quadratic formula. I could complete the square, but that would take a long time. So I think I'm going to try factoring first. And if that doesn't work, then I'll use the quadratic formula. So if the first term is 2x squared, I have to put a 2x and an x in my parentheses. If the last term is a 5, it has to be 1 and 5, and I'll just guess where the 1 and the 5 go. If I place the 1 and 5 like I have on the screen, my inner term is 1x. My outer term is 2x. I'm not going to be able to get a 3x out of this, even if I make one of them positive and one of them negative. So I'm going to switch around the 5 and the 1. So now my inner term is 3x, outer term is 2x. It's a negative 5, so one has to be negative and the other has to be positive. If it's a negative 5 plus 2, that does give me the negative 3, which is what I needed for that middle term. So that means the 5 is negative, the 1 is positive. So there are my factors. And then I'm going to set each of those factors to 0. 2x minus 5 equals 0, or x plus 1 equals 0. For the first factor, add the 5, divide by 2. X is 5 halves. For the second factor, we have to minus the 1, so x is negative 1. So I've got two solutions, x equal 5 halves, or x equal negative 1. So there are two different values of x that give me that same y value of 5. All right, the last part of this problem asks us to find f of x plus 2. So now our input is x plus 2. We're going to take that expression and plug it in for the x's. It's okay that there's also an x in here. All this means is when I rewrite my function, instead of x, I put in x plus 2. So when I plug in the x plus 2, I get 2, and then x plus 2 squared minus 3, x plus 2. So I replaced both of the x's in the function with x plus 2's. Then we can simplify this. We can expand x plus 2 squared is x plus 2 times x plus 2. That's an x squared plus 2x plus 2x plus 4, or x squared plus 4x plus 4 when we combine those like terms. And then we can distribute We distribute the 2 to the x squared plus 4x plus 4. And then I'm going to distribute the negative 3 to the x plus 2. So that gives me 2x squared plus 8x plus 8 minus 3x minus 6. Finally, if I combine like terms, I've got 2x squared, 8x minus 3x is 5x, 8 minus 6 is 2, and there's my final answer. We're not solving for x this time. We were just asked to take an expression, plug it into a function, and so our answer is an expression as well. And that's it. That's my final answer. One specific example of working with functions and doing operations of functions is finding something that's called the difference quotient. The difference quotient is defined to be f of x plus h minus f of x all over h. This difference quotient is going to be really important if you move on and take calculus classes. But for now, we're going to use this as an exercise of practicing this function notation. The difference quotient is an average rate of change. It's something a lot like slope, rise over run, change in y over change in x. But we'll talk more about that later. So for now, let's just do this operation. We're going to start by finding f of x plus h. So f of x plus h means we have to take x plus h and plug that in for all of the x's in our function. So f of x plus h for this function would be x plus h squared plus 3 times x plus h plus 4. So I replaced both x's in the equation with x plus h's. Now before I do anything else, I'm going to take the time to expand and simplify if possible. So I'm going to square the x plus h. We can use FOIL to do that. Or if we want to save a little bit of time, there is a pattern when you're squaring a binomial. You always get first thing squared, so x squared, plus double the first times the last, so plus 2xh, and then plus last thing squared, plus h squared. So x plus h squared turns into x squared plus 2xh plus h squared. Again, I could have used that FOIL, first, outer, inner, last, to do the multiplication. Then I'm going to distribute the 3. So that gives me 3x plus 3h, and finally plus 4. All right, unfortunately there aren't any like terms, so this long expression is my f of x plus h. And so now I'm ready to plug everything into my difference quotient. F of x plus h is the thing that I just computed. And then we're going to minus f of x. So I'm going to subtract the original function, which was x squared plus 3x plus 4. And I put that in parentheses to indicate that we're going to subtract that entire function, and that's all over h. So now I'm going to take that subtraction, that negative sign, and I'm going to distribute it to everything in the parentheses, everything in my f of x. So my difference quotient is now x squared plus 2xh plus h squared plus 3x plus 3h plus 4. That's my f of x plus h. And then minus x squared minus 3x minus 4. That's my minus f of x all over h. Finally, let's see if we've got any like terms, and we do. We've got an x squared minus x squared. That goes away. 3x minus 3x. That cancels out. 4 minus 4. That cancels out. And so we are just left with 2xh plus h squared plus 3h all over h. There's one more thing we can do to simplify this. I noticed that every single term in the top has an h in it. And so I can actually factor that h out of the top, and I'm left with h times 2x plus h plus 3. So I just pulled an h out of every term in the top. And now we've got a common factor of h. We can cancel that common factor, and we are just left with the expression 2x plus h equals 3. The last thing I'd like to run through in this video is the graph of some basic functions. We're going to call these toolkit functions. And later on in this course, we'll be expanding on graphing functions, and this is going to be our starting place. So I've got a list of 6 functions. Let's take a look at the graph of each of these. I'm going to start with f of x equals x, the first one. That is the same as the equation y equals x. That would be a linear function. It's a straight line. It has a slope of 1. The number in front of the x is 1. And it has a y-intercept of 0. It goes through the origin. And so on the screen, I have the graph of our linear function. It's a diagonal line that goes through the origin. That would be the line y equals x. Next, we have our quadratic function, f of x equals x squared, or y equals x squared. To graph this function, I've created a table of values. I've selected a handful of x's or inputs, some negative, some positive. So I'm going to do -2 to 2, and I'm going to take those x values, plug them into my function to see what the y values are. So if x is -2, -2 squared is +4. If x is -1, -1 squared is +1. If x is 0, 0 squared is 0. X is 1, 1 squared is 1. X is 2, 2 squared is 4. Then I'm going to take these points in my table and plot them. X is -2, y is 4. That's the point -2, 4. X is -1, y is 1. So -1, 1. The graph goes through 0, 0, 1, 1, and 2, 4. Now that I have a handful of points plotted, I can connect the dots, and I get this kind of U shape. This is called a parabola. Quadratic functions are shaped as parabolas. So the graph of y equals x squared looks like a parabola that goes through the origin. The origin is actually the bending point of that graph. We'll definitely go into more depth with quadratics and parabolas later on in this course. But on to our next function, we have a square root function. F of x equals the square root of x. So I picked a bunch of x values. I'm only going to pick positive numbers because I can't take the square root of a negative. I can take the square root of 0. Square root of 0 is 0. Square root of 1 is 1. If I plug 4 into the function, square root of 4 is 2. If I plug in 9, square root of 9 is 3. And I'll plot some of those points. So my graph goes through the point 0, 0, 1, 1. X is 4, y is 2. And then I didn't have room to put in that 9, 3, but I can kind of see what the shape looks like. We've got this curve that starts at the origin. Technically, this is half of a sideways parabola. So it's got the same kind of curvature as that U shape for our quadratic function, but it's sideways, and we only get half of it. Because with square root functions, we can only put positive x's in it, and our outputs are positive y values as well. All right, the third one on my list is my absolute value function. Absolute value means distance from the origin, or it takes a number and makes it positive. So if I plug negative numbers into the absolute value function, like -2, my output is +2. Absolute value takes a number and makes it positive. If I plug -1 in, I get 1, 0, 0, 1 stays 1, 2 stays 2. And if I plot those points, my graph goes through the point -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. In fact, when the x's are positive, the graph just looks like the line y equals x. But when the x's are negative, now the y values become positive. And so what we end up getting is something that has this V shape. Absolute value functions look like a V. We can plug positives or negatives into them, but our outputs are always positive. All right, the next one on my list is my reciprocal function, y equals 1 over x, or f of x equals 1 over x. And I've just drawn the graph of this one for you on the screen. I'll try to explain where this graph comes from. But this is what our reciprocal 1 over x function looks like. Basic idea is if you plug in x equals 0, you get something that is undefined. So there is no point when x equals 0. As you plug in bigger and bigger numbers, your outputs get smaller and smaller. So for example, if I plug in 2 for x, my output is 1 over 2. When x is 2, y is a half. When x is 3, y is a third. And so this graph approaches y equals 0. As x gets bigger, the y values get smaller. If I plug in super tiny numbers for x, I end up getting larger values for y. So if I plug in really tiny fractional numbers for x, my y values get bigger and bigger and bigger. And so this graph is also approaching x equals 0. Something similar happens on the other side of the graph. There's a kind of symmetry here. If the x's are negative, it means the y values are also negative. And so we get the same kind of shape, but in, we call this quadrant 3, where the x's and y's are negative. We're going to talk a lot more about what we call rational functions, functions that are fractions. But for now, let's just kind of remember this shape. Y equals 1 over x has this kind of basic shape where it's approaching x equals 0, it's approaching y equals 0, but it's never crossing or touching them. All right, I'm going to graph one more function. My last function is f of x equals x cubed. In this function, if you take a number and you cube it, if the input or the x is positive, you get positive outputs. But if the input or the x is negative, you get negative outputs. And so I've plotted a couple points. This graph goes through 0, 0, 1, 1, because 1 cubed is 1. And then it goes up pretty steeply. If you plug 2 in, 2 cubed is 8. And so we get something that curves kind of like our parabola, except it goes up to the right, and it goes down to the left. Again, because if you put negative x values in, you get negative y values or negative outputs. All right, there's many other types of graphs that we're going to work with, but I'll just start with these 6 in this video, and we'll expand on this topic later on. As always, if anything in this video is unclear, please reach out.